Okay, Adnan, the question in the assignment was this. You had to evaluate the antiderivative of 1 by x squared cos 1 by x dx. Yeah, so that's it. And you know that you can apply the substitution. 1 by x is equal to t, which gives us minus 1 by x squared dx is equal to dt, which then implementing the substitution gives us integral cos t into minus dt, which is trivial, gives us minus sine t, which you can back substitute to get minus sine 1 by x plus c. The question you asked was, can this be done by parts? So we have a couple of options. The first is we take 1 by x squared as the first part, and the second is we take cos 1 by x as the first part. So let's take 1 by x squared as the first part, and you get 1 by x squared integral cos 1 by x dx minus integral of d by dx 1 by x squared integral cos 1 by x dx dx. Yeah, this is just by parts, yeah, implementing that. So the question arises here because of this integral cos 1 by x shows up in both of the expressions. Can we actually evaluate that? So let us see what possibilities we have. So we are trying to evaluate integral cos 1 by x dx. So here we could attempt a substitution. 1 by x is equal to t, which gives us minus 1 by x squared dx is equal to dt, which then gives us dx is equal to minus dt by t squared. And so when we put that in the above expression, we will get integral of cos t into minus dt by t squared. And now we could say we'll evaluate this by parts, yeah, taking cos t as the first part. So we say, okay, I1 is cos t integral minus dt by t squared minus d by dt of cos t integral minus dt by t squared dt. Okay, that's again by parts. So that gives us cos t into 1 by t minus integral sine t 1 by t dt. And so we can proceed further by evaluating the second antiderivative using parts again, yeah, with the trigonometric term sine t as the first part. So then we get cos t 1 by t, and then applying parts here, sine t integral dt by t minus integral d by dt sine t integral dt by t dt. Okay, that's pretty straightforward there. Now, so what we get here is this is what we'll get. I1 will be cos t into 1 by t minus sine t log mod t plus integral cos t log mod t dt. Now this third term here presents difficulties. Yeah, if we take log mod t as the first part, that would just reverse the previous steps. Yeah, and we'll be going backwards to the original expression for I1 that we had. And if we take log mod t as the second part, we would have to evaluate its antiderivative. It's not difficult. We already know what it is. It is t log mod t minus 1. But what this does is it introduces a third kind of function into the integrand. So you'll have an algebraic one, the t. Then there's a logarithmic one, the log mod t. And we shouldn't forget that we have the cos t, which we will have to differentiate for doing parts here. Yeah. So that would have become a sine t. And so we have three kinds of functions in our integrand now. And so the integrand is far more complex than it originally was. And this is not an approach that looks promising. We could attempt to evaluate I1 taking cos t as the second part. And so what we get then is minus 1 by t squared integral cos t dt minus d by dt into minus 1 by t squared integral cos t dt. And that just gives us minus 1 by t squared sine t minus integral of 2 by t cubed sine t dt. And now it's evident that we can't really proceed with the second term here, simply because if we interchange the order of the parts, we would reverse the process. And if we continue with the same order, at each stage, it will give us an x to the power n term in the denominator, rather t to the power n term in the denominator of the integrand, with n incrementing by 1 every time. Yeah, and so this will, the next time we will get a t to the power 4, after that we'll get a t to the power 5, and so this will be a never-ending process. We could go back to the original expression, take cos 1 by x as the first part, and that would give us I is equal to cos 1 by x integral 1 by x squared dx minus integral of d by dx cos of 1 by x integral 1 by x squared dx dx. So that's applying parts with the order reversed there. And so that gives us cos of 1 by x into minus 1 by x minus integral sine of 1 by x into minus 1 by x squared into minus 1 by x dx. And that gives us minus 1 by x cos 1 by x minus integral of 1 by x cubed sine 1 by x dx. And again, it's evident that we can't proceed with this second term. Interchanging the order of the parts would just reverse the process. Continuing with the same order would just give us an x to the power n term in the denominator each time, with n incrementing every time. Yeah? So the next time it would be x to the power 4, and then x to the power 5, etc., etc. So the conclusion is this: we've tried all possibilities for parts for the original expression, and we conclude that it can be evaluated only by substitution, not by parts. And even the secondary expression, integral of cos 1 by x dx, cannot be evaluated by parts. The real bottom line is this: when should you be thinking of parts? Only if it is possible to split the original integrand into the product of two functions, one of which we will call the first part, is difficult to find the antiderivative for, but whose derivative is relatively uncomplicated, and the other of which, namely the second part, is easy to find the antiderivative for, and whose antiderivative is relatively uncomplicated, should we attempt to determine antiderivative by parts. Okay, so I hope that answers your question. The answer is no, but here's the more important conceptual issue that you need to consider when you are thinking about parts.